In this video, I'm going to review some foundation that's important for doing mathematical modeling. And the first piece of foundation we're going to review is working with exponential functions. The reason why we're reviewing exponential functions is that they arise naturally as part of the solution to a large set of differential equations. Equations that have this general form where the rate of change of an unknown quantity is proportional to the unknown quantity itself. So the rate of change of a population is proportional to the population. If you have more people, you're going to have more babies that are born. If you have more money in a bank account, and that bank account is being hit with a particular interest rate, then every month a proportionately larger amount of money will appear as growth from that larger base of money. So in addition to populations and in addition to financial calculations, there's a host of other real physical systems that behave according to exponential models like this. And a piece of notation here is that at time 0, we'll say that the population is y of 0. So if we say the population is given by y, then y evaluated at 0 is the initial population. And sometimes that's denoted as y subscript 0 or y sub 0. Just a notation thing. I'll use them interchangeably. Another notation that's sometimes used for initial population is capital A or capital P. Just different letters that all denote the same thing. So I mentioned that an exponential function naturally comes out of this type of model, and I'll show you that by solving this differential equation. dy by dt is equal to k times y, where k is an unknown constant. That constant k is something we'll get from data, something we'll get from additional information. Y is the function itself, the mystery function that adheres to this differential equation. And we're told that y of 0 is equal to a, so the initial population is a. This is a separable differential equation. What I'm going to do is I'm going to bring all the y stuff to one side, all the stuff that isn't y to the other side. So let's divide both sides by y, multiply both sides by dt, and then integrate both sides. Left-hand side, we have the antiderivative of 1 over y with respect to y. That's ln y. For differential equations, we'll drop the absolute values. On the right-hand side, the antiderivative of k with respect to t is k times t plus c. All right, now I'm going to exponentiate both sides, raise both sides as powers on a base of e. I'm going to use base e to get access to the cancellation law on the left-hand side. So e to the kt plus c. We get cancellation law, y is equal to. Now the next thing I'm going to do is I'm going to use an exponent law. I'm going to use the b to the m plus n is b to the m times b to the n. So y is equal to e to the kt times e to the c. Now the next line, what I'm going to do is I'm going to let, let's see, c equal e to the c. Now if that bothers you, let d equal e to the c. Just replacing it. If c is an arbitrary constant, then e to the c is also an arbitrary constant. I'm just going to call that arbitrary constant d, so it looks a little bit less weird. Y is equal to capital D times e to the kt. Now we're told that y of 0 is equal to a, so y of 0 is equal to d e to the k times 0. So a is equal to d times e to the 0. A is equal to d times 1. So that means d is equal to a. Our unknown constant is equal to our initial population. Thus, our population as a function of time is a times e to the kt. So let's say we start with 1,000 people. Maybe this is people, maybe this is bunnies, whatever it is. We would have y is equal to 1,000 times e to the kt. T is time. K is that unknown constant. It is a growth rate that comes from additional data. Data that we do not have inside this problem. Anyways, the important thing is that an exponential function came out. Now, I call it a growth rate, but I mean, it's more general than that. If k is positive, then it results in an exponential function that has this shape. So exponential growth function. But if k is negative, then it's going to be a decay function. The graph is going to look like this, exponential decay. Despite this, decay is in general called the relative growth rate of the function. Now, I said that we will get k from data, but there are some problems where you can infer logically what k has to be. But for the most part, it's data. It's stuff you get from experiments, stuff you get from a statistical analysis of other data sets. All right, and I said that we're going to review some properties of exponentials and logs, and it's kind of what we've already been doing. It's looking for opportunities to use a cancellation law. So e to the ln of a is equal to a, and ln of e to the a is equal to a. So whichever order you write them in, exponentiating and logging are opposite operations. You put them back to back, it's like nothing happened. And the other operation that we're going to work on is evaluation. And then we'll talk about solving, rearranging in the next slide. All right, so in this problem, we're asked to evaluate the function y equals 10 e to the x at different x values. At first, we want at 0. So we're going to have 10 times e to the 0, replacing x with a 0. So it'll be 10 times anything to the power of 0 is 1. So 10 times 1, which is 10. Next one, we're evaluating at x equals ln 3. So we'll have 10 e to ln 3. We can use the cancellation law. So 10 times 3, which is 30. What if we have twice ln 3? So we have 10 times e to the 2 ln 3. Is that going to be 60, or is that going to be something else? Well, we can't cancel the e ln. The reason we can't cancel is that there's a 2 in front, so we're going to have to use a log property. We're going to use a property that allows us to bring a coefficient in front of the log function up as a power inside the argument of the log function. So we'll have 10 times e to the ln of 9 to the power of 2. And now we can use the cancellation law. Oh, my apologies. It's a 3, not a 9. 3 to the power of 2. I think I must have got ahead of myself. So we have 10 times 9, which is 90, not 60. So we put this 2 here. We doubled the argument of the function, and we did not double the output. We went from 30 to 90. We tripled it. Okay, now what about if we don't put a 2 in there? What if we just keep it as a t? So what happens in that case? We'll have 10 times e to the t ln 3, and we can't use the cancellation law, but we can bring the t up as a power. 10 times e to the ln of 3 to the power of t, cancellation, so 10 times 3 to the t. And we cannot write that. This is not 30 to the t, but 10 to the t times 3 to the t is equal to 30 to the t. So just gotta be careful when you have two terms multiplied together. You can't combine them into the same, you can't combine them into a new base unless both of those terms are raised to the same power. 10 is not raised to the power of t, or the example that we have, and the 3 is multiplied, or not multiplied, is raised to the power of t. So they're raised to different powers. We can't combine the terms. The important thing what happened inside that last example is we took an exponential function, e to the t ln 3, and we used log properties to rearrange it. We got rid of the e, or the ln, we just replaced it with an exponential function that had a base of 3 instead of a base of e. That's a very common trick that we're going to do for these types of exponential models. Okay, as promised, the other thing that we're going to do a lot of inside this part of the course is we're going to be solving for unknowns, solving for a variable, rearranging the expression to extract what the unknown is. So in this first example, we're asked to solve for t if 10 times 2 to the t is equal to 250. Once in a while, a nice number will come out, but more often, a not very nice number will come out. So let's see what happens here. Whenever we're solving across an equal sign, we have to make sure that we're doing the same thing to both sides of the expression. And that might be subtracting a number from both sides, dividing both sides by a number, multiplying both sides by a number, logging both sides, or exponentiating both sides. And the way I'm going to start this one is I'm going to divide both sides by 10. So 2 to the t is equal to 25. I can't divide next. I can't do any more divisions. If that wasn't a 25, let's say if that was a 32 or a 16 or an 8 or something, then I could write that number as 2 to some power, but I can't write 25 is equal to 2 to some nice power. So what I have to do next is I have to make a choice. How am I going to express this t value in terms of logs? Am I going to use a natural log? I'm going to take a ln of both sides. So the ln method and the log not base e method. All right, so the ln method, which is kind of a more natural choice, I think, is I'm going to take the ln of both sides of the expression. So the ln of 2t, or 2 to the t rather, is the ln of 25. Then I can bring the t down. T times the ln of 2 is equal to the ln of 25. And then divide both sides by ln 2. So t is equal to ln of 25 divided by ln of 2. By the way, this is not the ln of 12.5. You can't divide across log functions like that. Ln of 25 over ln of 2 is not ln of 25 over 2. If you plug it into a calculator, it'll tell you approximately what t is equal to, and it has to be larger than 4. 2 to the power 4 is 16, so it's got to be larger than that, and smaller than 5. 2 to the power 5 is 32. So you've shot past 25, you've gone too far. So it's got to be somewhere between 4 and 5. And if you plug into a calculator, it'll tell you exactly what that number is supposed to be. All right, how about the not base log? Well, sorry, the not log base e. Well, what other log bases could we use? And the truth is we could use any base, log base 7, log base 25, log base 5. But log base 2 is, I think, going to cause the greatest simplification. If we take log base 2 of both sides, we can use a direct cancellation law on the left side, and we get t is equal to log base 2 of 25. And you might look at that and say, oh my god, why didn't you just start with that? Why did you do the hard one first? Why didn't you do the easy one? And the reason is, well, if you have a calculator, the reason's going to be staring at you. Your calculator does not have a log base 2 button. And it's even in typical software implementations, math engines, logs of weird bases are calculated in an inferior way compared to logs of base 10 and base e. So when feasible, express logs in either of those bases. Typically base e is the best. We'll do the same process for the next problem. Here we're not asked to solve for t, we're asked to solve for k, but it's the same idea. I'm going to rearrange first by dividing both sides by 250. So 1000 divided by 250 is equal to e to the 3k. So 4 is equal to e to the 3k. I'm going to take the natural log of both sides, so ln both sides, ln 4. I'm using ln because I have an exponential function with a base of e. And that will, on the right-hand side, allow me to use the cancellation law. Left-hand side, I'm stuck with a ln 4. So ln 4 is equal to 3k. And then we can divide both sides by 3. Thus, k is equal to ln of 4 over 3. Now, as a warning, we can also write this as 1/3 of the ln of 4, which we can then write as the ln of the cube root of 4. Well, I'll do it in 2 steps because that's maybe confusing. Ln of 4 to the power 1/3, right? Using that log property, bringing the coefficient in front up as a power. Now what can we do? Well, what does 1/3 power mean? It means cube root. So they're all equivalent. Ln of the cube root of 4. Now, there wasn't much utility to doing all that extra work at the end there because 4 doesn't cube root nicely, but if that was an 8, that'd be pretty nice. Okay, in the next video, we'll look at applications.